why blindsight patients lose visual consciousness after V1 lesions? And can the properties of V1 explain it? So in summary, V1's role for visual consciousness is still unclear, unfortunately. And we are now starting to get into the sort of the frontiers of the research gradually. This relates to the core research questions for consciousness. And we know a lot about the properties of the V1. So just by knowing what the V1 neurons are doing doesn't tell us directly about our, clue as to what the relationship is between the neural activity and consciousness. And for example, the property of the V1 is that the topographically organized and also it kind of represents the external world in a retinotopic manner. And these terms will be defined in this lecture. And so for the rest of the, the video, let's assume that V1 properties mirror our visual consciousness. And if that's the case, does it actually make sense? That's a question. So this is the visual field, definition of the visual field. If you look at the display at this location, for example, at the cross, red cross, then depending on the distance onto this display, there is a blind spot if you are seeing it with one eye, and then that part is receiving only axon, so it doesn't detect the photoreceptor, doesn't detect the lights, so it is filled in by percept. But anyway, and then once there is a binocularly observed regions here, which is visible for both left eye and right eye, but there are some areas that is only possible to see with the right eye here. That's something that I cannot see with my left eye. Okay. And how does this map onto V1 areas? That's a question. So the answer is something like this. V1 is, if you unfold it, it looks like a rugby ball kind of shape. It is ellipsoid. And even though the outside of the world is this sort of half circle here, it's mapped onto this, round ellipsoid. So there is some kind of transformation from here to here, and it's been worked out quite a bit mathematically already in the computational neuroscience field. And here the important concept is retinotopy. What it means is that the retinal topographic organization is preserved in the visual cortex. Topography means that if something is close to another things, then its distance relationship is preserved after the mapping. That's probably enough definition for now. And then another thing is that the cortical magnification. So what you notice immediately from here is that something that is depicted as very, very small circle or triangle here corresponds to big extent here. That's up to 2.5 here, see? And then 5 degree of the visual angle that occupies up to this one is mapped onto the V1 here. And then the most peripheral area, like 40 degrees of the eccentricity, is occupying at here. And then up to the largest, sort of the extent of the peripheral vision is compressed to be presented here. So this corresponds to cortical magnification. It's almost like magnifying the fovea at the level of the cortex. Okay. And how does it happen is the next question. So as I said in the last video, both of the eyes can see left side and right side of the visual field. And right side visual field goes into left visual hemifield, primary visual cortex. And so if you're looking at this kind of movie screen with fixating at this, red cross, and then let's imagine that the left side of the screen is on the red and the right side of the screen is green. Then respectively, these projects on the left side of the retina for the green one, and the right side of the retina with the red one, and that projects as as a side of the visual cortex. So the green visual field on the right side is now projected on the left visual cortex, and the red one goes into the right visual cortex. Okay, and so at this point, I want you to ask, what happens in the brain when you see this, GAR, when you are looking at it, at her nose, for example, here, by your eye? What kind of visual information is projecting on your V1? That's a question. So, based on this anatomical, architecture, that right visual field eventually projects onto left visual cortex with this kind of rugby ball shape. You can imagine, but what happens is something like the following. So outside image is this, guard like this. And then you are looking at the number 5 at the nose of the guard. And then on the retina, already, because of the lens property, image is upside down and the left side and the right side flips. This is nothing to do with the eye itself, but it's just the optics of it. And so camera also has the same kind of property. Okay, the right side, left hand now projects onto the right side of the retina. And then the side is kept onto the left visual B1, and it's magnified at the location of the fovea. So fovea is around here, right? 5 to 6 and so on. And then periphery of this hand gets projected into this very small thing. So this is because left visual field, this side is a fovea, and then it enlarges this small part of this face largely, and then this peripheral hand becomes very small. Okay, and similarly, if you show this kind of figure of the Simpsons, then left and right visual field, V1 will see this image like this way. And as I said here, sometimes I noticed that the web resources are wrong about this basic kind of facts. So just be careful, but come back to this depiction. That should be correct. Okay, so in summary, left or right visual primary visual cortex V1 represents right side of the visual field, or left respectively. And then don't confuse this with your eye of origin. Left eye and also right eye both can project onto the right hemisphere or left hemisphere, depending on which visual field you're talking about. Okay, and V1 has a topographical organization. So close thing gets projected to close location in the visual cortex. Neurons in at the foveal areas have a smaller receptive field. So that's still correct. Okay, although the number of the neurons gets reduced in terms of as you go into the periphery, still each of the neurons' receptive field becomes bigger. Okay. So this is called cortical magnification. Cortical representation of the phobia is huge in V1. Up to 2.5 degree visual angle corresponds to 20 to 25% of V1. 10 degree visual angle occupies up to 50%. So this kind of argues against the idea or claim that I defended for seeing why we can see the peripheral vision, right? So even though each of the neurons in the periphery can have a large receptive field, the number of the neurons that represent it is also smaller. So that may also lead some to believe that cortical peripheral color may be illusory, but for the other reasons, it's not the case, most likely. Okay. So then as a final slide for this week, coming back to the blind side and V1 issue. So assuming that the blind side arises because of the lack of the V1, if we assume further that the conscious experience arises or mirrors the property of the V1, but then that sounds a bit strange for many reasons. One is that it's upside down, and nobody knows how it's corresponding to our upright visual areas, visual experience. And the second is that phobia is hugely enlarged, but our experience is not like enlarged phobia. Okay, and so it's not like V1 is sort of a screen of the our experience, and that's the kind of the criticism that Daniel Dennett made a brief reference in his interview by Sean Carroll. He said that there cannot be Cartesian theater. Cartesian theater means here that V1 is acting like a screen. That's not the case. But then, so V1 activity or V1 structure itself is not responsible for conscious vision, in a simple, one-to-one mapping. But what is the exact relationship between V1 structure and also neural activity and the conscious vision is still unclear. And that's the reason why I said that, the V1 vision, V1 property and the blind sight is one of the core and also the front of the consciousness research. It has been like that, and it will be like this for a while until we understand sort of mapping between phenomenology and neural activity or information. And that's the kind of the topic that will go over the next couple of weeks. All right, that's it for this week. See you next week.